And so I think everybody can see my presentation now. So I see NSU. Could you raise your hands? You can see the presentation? All right, great. Thanks, guys, because I can't see what you see, you know. Actually, it's pretty interesting to run this software. It's like a Skype thing called Zoom. And there's like chat boxes, annotate boxes. It's like flying an airplane or something. When you're a presenter, there's a handful of things that are going on at once. So I try to keep track of the students, et cetera, and all the other things here. So anyhow, let me start with the presentation. So good morning. This is, June 2019, and what we're doing here for a summer, per se, experience for a lot of students, what I'd like to do, or my assignment is, to overview contact lithography. And what is lithography? I mean, I think we should have a definition here. Lithography literally means writing in stone. So this is what we're trying to do is we're creating a pattern. And what I always think about, like this writing in stone or some other analogy that we can take a look at so that you guys can understand what we're going to talk about today. This is like a pattern generation thing. And let me do like a little story here, which has nothing to do with nanotechnology, so you can see what we're doing. So say you live out in the country and you have a mailbox. So on your mailbox, you always want to like put down your house number or your name or something like that. So generally what you would do out in the country is you'd get a piece of cardboard and you'd write the letters of your name or your number of your street, and you cut them out with a razor blade, right? And then now you have this pattern in a piece of cardboard, and that's like your template. And then you put that up against your mailbox, and then you get some spray paint and you spray it on there, and it goes through the exposed area and it goes onto your mailbox, and therefore you transfer this pattern from the mask, which was your piece of cardboard, onto your mailbox. We're doing something very similar to that. What we're trying to do, our wafer would be like our mailbox, and lithography or photolithography is the way that we're going to make. We don't have a piece of cardboard. We're actually going to use an organic polymer that's not going to use a knife to cut out the letters. We're going to use this organic polymer, and the organic polymer is photosensitive, that it's going to change its properties wherever we shine light on. So there's like an intermediate step, not that spray paint can, but there's going to be like light that shines on my piece of cardboard by the analogy that I'm going through. And what that's going to do is like break down the bonds, or it's like my knife cutting out the circles. Does everybody understand that? So basically that's what I'm doing. And I have like purposely, a fuzzy picture here on my introduction for contact lithography, and this shows the pattern. So this is what we're going to do. We have our substrate. We put down our mask, which is our photosensitive chemical, and then we're going to shine light through it. And then that light is going to make or break bonds, and then we're going to wash that stuff away, and then we're going to be able to do either deposition or etching at that point in nanotechnology. So this quick picture here that's on the cover, just this artistic rendering with the link down below, that just shows basically what we're going to go through today. And I'm real happy to give you this presentation. Well, I'm happy to be a teacher, right? But, I'm happy to give this presentation because I'm like allocated a good amount of time to do it. So while it might be a simple process, there's a lot of details in there, and that's what we're going to do. So we're going to do maybe two things here today. We're going to look at the 10,000-foot big picture of lithography, but we're also going to look at each individual step and the details of each individual step. Another thing during this introduction I'd like to convey to you, why is this important? Well, contact lithography does moderately larger features for micro technology, but the algorithms that we use here are the things that we would utilize in modern manufacturing and things like high performance steppers. So this pattern generation method or algorithm is the same thing that makes all the parts in your cell phone per se. So this is really important. This isn't some academic exercise or is not used. Without this pattern generation method and without lithography, you don't have computers, you don't have cell phones. So what's interesting about that, so again, as background before we start the presentation, I got to ask you, or what you should be learning here over the summer is, how big is a transistor on a cell phone, like on a microprocessor, and the gate dimensions on a transistor are submicron. So we're trying to make things, like a typical gate might be like 0.08 microns or 0.12 microns or some level like that. And that number comes from the light source, usually a laser. And that laser, a wavelength is going to give us our resolution of our lithography. So we match our masks to that, and that's our base dimension. And that base dimension is as big as a virus. Does everybody see that? So it's impressive. This technique, we can make billions of times over to make transistors on a microprocessor, and they're as big as a virus, and it's really robust and reliable that we can perform this process and be able to make things like Pentium processors or A5s or A7s, whatever's in a cell phone nowadays, like an Apple phone. I think they're A7s or something. I don't keep up on that stuff. They used to be A7s. Probably something new because they get more expensive every year, so they have to rename them at least. So that's what we're doing here. So I wanted to give you a background in what lithography is. So what lithography is, we're going to take a wafer, and then maybe I'll go to some pictures here, and maybe I'll be able to show you better. So let me go on with the presentation. So what I'm doing now is this is my outline for today. I'm going to give you the general information and an introduction. That's what I'm trying to do now, is set the presence for what we're going to do over the next couple of hours. And then this is basically, you look at the other steps that are shown here in the black. These are the standard steps in lithography. So you go through these steps, and then when you go through these steps, you did the process. And what's good about these steps in some ways, taking a couple steps back, when we look at this list, this is the same steps in some ways, or the algorithm that we would use in like high performance steppers, etc. And that's really important. So we're going to learn a lot here. And this is the standard way of doing, the very, very standard way of doing pattern generation in nanotechnology today. Interestingly, from an education perspective, now this is the standard, and this is how certainly 90% of the things that you own are done with this method. When you understand this method, like as an academic exercise or a teaching experience, we could look at other methods that are completely different. So we'll use this method as a reference. Does that make sense to everybody? So this is very, very important. This is the standard way of doing it. But when we know the standard way, we can also look at unique ways of doing pattern generation. And I'm not assigned to teach you that, but this is how I teach my classes here at Penn State. This is the standard because this is what most people do. And once people understand this, they can understand other ways that are unique. So you can use this to contrast other things. So this lesson, or today's understanding, I think is really important to you for a few reasons, and I think as an engineer, you have to see these things. Often we learn algorithms, but we also learn to contrast those algorithms so we have references, and it makes other things easier to learn. So that's my education message for you today. So again, this is my outline, the general information, which I'm going over now, and these are the per se standard steps, and we're going to look at these in detail throughout the presentation. Each individual step we're going to break down and understand the nuances of it. But for the most part, you could probably perform this method when you would go into the lab, like in your nanofab or in our nanofab or something. You could probably do this process in certainly under 10 minutes. And we're going to take 2 or 3 hours to discuss this. But in essence, when you know how to do it, it only takes a few minutes to do, but we're going to look at a lot of the details. So there is a lot of really good information here that we should go over. So this is a quick overview of what we're doing. So I always like to, show where is our objective? Where's the bar, or where are we going to? So, if you're hiking in the woods or something, a lot of things that you would like to do is, you have a map and everything, but you probably point to a mountain or some other feature. That's where we want to get to. So this is where we want to get to. So basically what I'm going to do is the drawing on the left, that's what we're going to describe today. So the one that has the red color to it, we're going to prepare the wafer, And when we prepare the wafer, what we're going to do is make sure it's clean, make sure we have the appropriate adhesion properties. Then what we're going to do is we're going to apply our photoresist, and the photoresist response to a mask. And that's going to be somewhat like my piece of cardboard that I cut my initials on. Does that make sense to everybody? And then what I'm going to do is when I apply that, I'm going to apply on a spinner, and I'm going to put my wafer on there, and I'm going to put a liquid on, then I'm going to spin it, and it's going to be coated uniformly across the wafer. So this is kind of like, I mean, well, cooks do this in some ways. If you ever watch them make cakes, like on the Food Network, they get the icing on a cake, and they flop it on the top, and then they have a rotating thing, and they spin it around while they get the knife, and they put the icing on the top of the cake and on the side of the cake real uniform. Does everybody do that? So you should know how to make a cake too. That might be more even important than nanotechnology. So you should know how to make a good birthday cake or something on your own. So that's how you would put that resist on. You like spin it on and smooth it out. Does that make sense? We don't have a smoother in this case by that analogy, but we just put on the liquid, then we hit a spinner, and it uniformly coats across the wafer. Does that make sense? At that point, we're at the thing that says pre-bake. The resist is on there, but the resist is wet, and it's an organic polymer, so I always describe it by analogy. It's kind of like a tar and kind of like nail polish, kind of like that stuff, but it's photoactive, right? But just so something that you would know as a reference. So if we would put my mask right on top at that point, it would stick. Does everybody see that? So it's like wet nail polish. So what we're going to do is do what we call pre-bake, and that's going to dry the wafer out. And now that we do that, we can do the next step, which says align and expose. And that's my mask that's going to have my features in it, like my letters of my name. And I'm actually going to place that on the photoresist. And the photoresist is dry at that point, so that my mask, my actual mask that I'm going to do my pattern, that my pattern's written on, it doesn't stick to the wafer. Does that make sense to everybody? So that's why we have the pre-bake in there. And then at that point, what we do is an align and expose. And the align is a tricky word because there might be made, and now we're making another layer of the transistor. Because we make transistors, they're kind of like making a torte cake or a hoagie, like many levels, like a complex peanut butter and jelly sandwich, right? So that's what we're trying to do on here. So we usually align that to pre-existing transistors, and that's what the align is. At that point, what we do is we do a light exposure, and it's a specific light that's tuned so that it makes or breaks bonds in the photoresist that we applied. At that point, what we did is we locally changed the chemistry through light, a chemical reaction, so that's an E to the KT, a photo reaction, locally where there's the exposure in the mask. Does that make sense to everybody? And then what we're going to do at that point, we're going to do the next step, which is the develop. And what the develop does is, for our case, if we were looking at what's called positive resist, we're going to be able to wash away. Does everybody see there was a lot of resist at this point? And then we do the develop, and then what that's going to do is wash away the bonds that were weakened in positive photoresist by the photo generation. And then we do the develop at that point. And then what we would do from there, we generally harden it, which is not shown in this quick drawing. And then the next step we see is etch, implant, etc. So that's the point where we might do an etch or an implant or maybe a deposition. And in my analogy from before, that's when we're actually going to have, this is going to look like we have the stencil applied to my mailbox, and then we're going to spray on some paint and leave our letters. We could also do in the mailbox, but we probably wouldn't do this. We could take my mailbox and then spray on like a mild acid, and then it might etch that pattern a little bit into my mailbox. Does that make sense? It would like change the metal or rust the metal or something on my mailbox thing, that analogy I talked about before. But we could also do, that would be the etching part, or an ion implant, because I know other people have talked to you about making a transistor and doping and all that. So that would be our dopant mask and stopper and stuff like that. And then finally, what we'll like to do at the end is we always remove the photoresist so we can do the next step. So the lithography at large is kind of like a transitional step that we do temporarily that we use to define the pattern. And once we define the pattern, then we have to clean off the photoresist and start a new pattern to go to the next level. So I'm sure that you know when we build something like a transistor or a Pentium microprocessor, it kind of looks like the skyline in New York City. We're building things up a level at a time. Does everybody see that? So when we're done with one level, we clean up that level like the photoresist and remove it, and then we start a new level. So basically, that's my presentation for today. So I wanted to make sure that you guys know what we're doing. So what we're going to do is we're going to go through each step, like prepare the wafer, and we're going to talk about that in detail. So I'm looking at, I can see the NSU people in there. I don't see anybody else because they don't have their camera turned on. So the NSU, you're my guinea pigs today. So you're my guinea pigs, guys. So be happy you're guinea pigs. So I'm looking at the thing. Does everybody understand that? We're all good? So raise your hand if you understand. All right, we're good. I see some hands in there. So go up to the microphone and stop me and interrupt me. Does that make sense? So that we understand. So I'm not trying to do a presentation today. I'm trying just to teach you. There's a difference. Does that make sense? So I'm not here just talking. I really want you to understand what I'm doing. And at some point, I might go a little too fast, or maybe you're thinking about lunch or something and you get distracted, or say, boy, this is a really good chocolate milk this morning, and you might not be able to focus at that second. So that's okay. I can go back and repeat things. So I always like to, at least I see successfully to teach, you usually have to say things 3 times so everybody gets everything. So I certainly don't mind repeating myself. And if I only do something twice, maybe you need that 3rd time. So please, please ask questions. Does everybody see that? So I'd really appreciate that, because I really want to have 100% of you knowing, possessing the knowledge in this presentation today, because it's really helpful. I'm saying this is how we make a lot of nanotechnologies. Does that make sense? This is a foundational technique that you really should know, and it's a foundational technique that you're probably going to be asked about in a job interview if you're in some kind of semiconductor market or making sensors or something like that. People really want to know this. So it's vital stuff for you guys this summer to learn. So please, let's work interactively so you understand this. So let's go again. Again, I'm going to do this 3 times, right? So contact photolithography is one of many types of photolithography that uses a mask to pattern the substrate surface. And this is kind of confusing because the mask is actually a quartz glass thing with chrome on it, and that has your pattern in there. For example, like your name on the mailbox. But that's our contact mask, right? That's our quartz mask. We also put a photoresist mask on the wafer. So this is moderately confusing because we have the hard mask, which is our thing that we made in e-beam lithography, and that has our permanent pattern on there. But we also put a temporary mask on the wafer itself. So let me go back up to that drawing. So here's my mask here. Let me get my annotate button out here and draw. So I'll draw a line or something like that. So I'm looking at this thing right here. Does everybody see? This is my mask right here, or this is my mask right here. I'm circling in the blue. That's the thing that's a piece of quartz, usually with a chrome that blocks light, and then where the chrome's not, the light will go through the quartz. Does that make sense? So that's my mask. That's my permanent mask. But also when I do this part down here, which is very confusing, now this becomes my temporary mask, my photoresist pattern transfer. They refer to that intimately as a mask once it's on the wafer. Does that make sense? So I don't know why, somebody just didn't invent 2 different words, or why people refer to that the same. So these are both called to be a mask. This is a hard mask, and this is in manufacturing. And then this part right on here begins this is my masking like agent, my photoresist once it's patterned. And then I could use that as a mask for etch or implant or deposition at that point. So that's my temporary mask. And again, going to strip this off later on. This thing up here, per se, this thing right here is my hard mask. Does that make sense to everybody? So let me see if I can. Now I got to hit X out of here. Oh, now I got to go back. I like my other software package that I have. Oops. So now I got to go to this annotate thing again. And I got to find eraser, which is a pain in the butt. I got to erase all this stuff. The other one just stays on an individual slide. This one, the drawing stays on the screen, so it would be on there all the time. So I actually prefer that other software package that we have. I record these lectures in another place for the summer course, and software is a little bit different. I like that one better. So anyhow, this is contact photolithography. It uses a mask, and again, that word tends to be confusing. This method involves a contact aligner that clamps the mask, which is our piece of glass, and the substrate together in a tight seal before exposing the substrate to ultraviolet light. And what that ultraviolet light's going to do is chemically change the photoresist that we extended on the wafer. Does that make sense to everybody? So we would use the most common. There's other tools that are available, but the ones that are like the standard. So like here in Pennsylvania, we have standards, right? So we don't call chocolate bars Cadbury bars or whatever. We're Hershey. So this is like Hershey, PA. We make Hershey bars. So that's the name brand, and that's what people used most of the time. And we say things like that, like for tissue paper, we would say Kleenex. So most times the industry that is most prevalent there, they would be the standard contact aligner in lithography. And probably the most popular one is a German company called Carl Zeiss. So Carl Zeiss makes the machines that most people would use for contact lithography. And the machines themselves, like this number MJB3, this tells you about the machine if you understand their catalog. And the 3 on the end tells us that it would work in a 3-inch substrate. And then this is an A6, which is a different type of system. The A means it's more automatic, and it would work on a 6-inch wafer platform. And the mask itself is usually an inch bigger, so that it would be a 7x7 mask for a 6-inch round wafer. And so these are the standard tools that most small companies would use. So companies under 50 employees would probably buy a Carl Zeiss. And a Carl Zeiss contact aligner, and you should know these things, they're probably a few $100,000, maybe $300,000, maybe $400,000. And those are the standard, and they have a limited throughput. They don't do many wafers in an hour, maybe 10 or something like that in an hour. I don't know. Depends on how fast the workers are, but and how you're dividing the work up. But they're not that fast. They're more of a manual system or semi-automatic system. An industry to do the throughput to make Pentium chips and to supply the cell phone market, they would use steppers. And those steppers are robotic and very, very fast. So what do you get for very, very fast? And to this rather rudimentary system, the Carl Zeiss does a limited amount, and maybe they're 300,000. If I were to go buy a stepper, a modern stepper, I would say give me a duffel bag, well, really big duffel bag I'd put on my back, and I'd say $100 bills, all unmarked $100 bills, right? Like I'm making some kind of deal. I'd have like a duffel bag, maybe 2 duffel bags, I don't even know. But a stepper is going to be like $35 or $50 million. But it's really, really fast. But it does basically the same process that we're going to discuss today as the contact aligner. What it's going to do is smaller feature sizes, and we're going to discuss that in the presentation. And it's going to do them really rapidly so that we can do, cassettes of wafers really, really fast, so we can supply like the cell phone market. So when Samsung comes out with a new phone, they have to, within a couple months, they got to make all new processors or whatever for them. So they got to, supply millions of chips. And so your machines have to be rather quick. So you wouldn't use a Carl Zeiss to do that. You would do that at a smaller company that would make something that wasn't so demanding as like cell phone parts, that there's a big market. So they might make some kind of other things like, I don't know, smoke detectors or something like that. So that might be good for this kind of market. So I wanted to describe these tools. I think that's important that you get that insight. Does everybody see? So these are things that I really want to talk about today that give you some background, because my discipline, or certainly your understanding, is academic, but it also must bridge into what does industry need. Does that make sense? So your knowledge has to satisfy the marketplace, right? So I'm talking about manufacturing at the same time. So to understand what machines cost and how fast production is, that's manufacturing, and those are things you really should know about. So these are contact aligners, and on the left is the MJB3, and I think you could probably buy a refurbished one of these for maybe $50,000, $60,000, and then a new system like a Carl Seuss MA6 here. The last time I bought one was a number of years ago, but I think it was something like, it was on to $300,000. But there's options on here that you can get, like different cameras and whatnot, backside alignment and those kind of options. But those machines are generally hundreds of thousands of dollars or so. And a stepper, which we'll talk about later, is certainly tens of millions. Does that make sense? So orders of magnitude, these Carls, like an MA6, generally cost what a middle-class home is, or an upper middle-class home. But, a stepper costs like what a neighborhood costs. Does everybody see that? Or a housing development. So it's a lot of money. So there's a big difference in those tools. They perform the same function, but a stepper generally performs things at a smaller level, like smaller devices for like microprocessors, and certainly does them rather quickly. And for the most part, if you would divide, like as a manufacturing concept, a stepper actually gives you a better return on your money. It's more cost effective than these cheaper tools. So that's something, let that sink in. The one that's $35 million is actually cheaper. And if we would use this one, although the initial cost is less, our devices would be a lot more expensive. So that being able to do things fast is really, really important. So these are kind of like the 9 basic steps of lithography. So again, here's a picture on the side to give us some dynamic picture in our mind that this is a flow, right? Like a process flow. So what we're going to do is we clean the substrate, and then we apply something called HMDS, and we spin that on and then do a bake. And what HMDS basically does, and so let's go back and maybe give you some insight into lithography and talk about these in detail. What the photoresist is an organic polymer. So my question to you is, what's an organic polymer? And a good organic polymer might be like pizza or cheese or oil that's on cheese and pepperoni that floats on top of your pizza. Does that make sense? So I think of organic polymers to be like an oily substance, maybe. Does everybody see that? So that like tar, nail polish, oily kind of thing, that's what my photoresist is going to be. Does that make sense? So if I had a substrate like paint is like that too. Paint is like an oily kind of thing. Does everybody see that? Like a spray paint can. Does everybody get the analogy? So spray paint is like that. So I'm going to ask you, and I hope you know the answer here, would I paint my mailbox if it was raining outside and my mailbox had a bunch of water on it? And then I walk up with my oil paint and spray paint it on top of my wet mailbox. Well, the paint's not going to stick. Does everybody see that? So this is the same analogy in my photoresist. My photoresist is an organic polymer, so it's very similar to, it's a photoactive paint. But my wafer, you might not think this, there's always humidity in the air. And my wafer has like these dangling bonds on there, so that water vapor actually sticks to my wafer. This is similar to when you're in a bathroom and you take a hot shower, your mirror is cold and you see a bunch of this, it's all foggy, right? The water vapor sticks to it. Well, in that case, if we took a spray paint can and spray painted over top of my mirror, the spray paint wouldn't stick. Does everybody see that? Well, you wouldn't think of that, but on the atomic level, this is my analogy, on the atomic level, basically my wafer is wet from the humidity. So what I have to do is I apply the HMDS, and what that does is it removes the water vapor from my wafer. This allows my photoresist to stick. Does everybody get that? That's what I'm trying to do. And then the next step, which is I don't know why number 2 is in there. I know why that number. So that's a typo. What I did is, this was just on a sheet, these steps. I put this picture in yesterday. So when I edited it, I made a mistake. When I was hitting the tab button, it always did that 2 redundantly. So I apologize. That 2 in there is a typo. I didn't review it properly when I added that picture. So step number 3, though, when we go ahead, then I'm going to put my organic polymer, like my spray paint kind of thing, on the wafer. And that's why we have step number 2. The wafer has to be really atomically dry. Does everybody see that? So that's what HMDS does. It atomically dries it. And it actually, step number 2 sets up the step that it has an adhesion promoter on there. So it's kind of like, it dries that. It's kind of like when you paint, you usually apply a primer. The HMDS is also a dryer and a primer at the same time. And then what we could do is, in step number 4, we soft bake, because the photoresist in step number 3 is wet, like wet nail polish, like wet tar, like wet paint. And we want to dry that out, because if we put my mask on top of wet paint or the wet photoresist, the mask will stick, right? And we can't have that. So we do a soft bake, and what that does is dry out the wafer. And then we put the mask on. You can see here on the right. We put that on the wafer, and then we do my alignment. Like I said, we want to do an individual transistor that's as big as a virus. And then from there, what we're going to do is our UV exposure, and that's going to break the bonds on the photoresist, because the photoresist is a photoactive compound, and then it's going to weaken those bonds in that area. Then what we're going to do with our developer is we're going to remove the resist that had the weakened bonds, and then we do a quality check with our microscope to see that everything's good and everything's lined up. And then we're going to do our process, like my etch or my deposition or whatever the next step happens to be, my next process step. So what we're doing with the photoresist is defining that process step. And then importantly, sometimes people leave this out. Then the resist, we don't need it anymore, because we did my procedure, etch or deposition. We have to remove the resist. Does everybody see that? So in some crazy conceptual way, we really want the resist, and we're using the resist, but after we're done using the resist, it's kind of like an empty water bottle. It begins something that we have to recycle or get rid of. Does that make sense? It's of no use to us anymore. That packaging or that layer, we have to remove. So the resist itself becomes a potential contaminant for the next step. So we have to remove it, really. And I'll give you this right now as a hint. The resist is, we talked about an organic polymer. So you guys should know from your chemistry, organic polymers are carbon and hydrogen generally, right? And then other things. But their backbone is a C and H kind of deal. Does that make sense? So my question to you, a rhetorical question, is, how do I get rid of these C's and H's, my photoresist that's left in step number 9 on my my photoresist is made out of carbon and hydrogen. A good way to chemically do that is, in some ways, add excited oxygen to that. And then my carbon and hydrogen will turn into CO, CO2, OH, and H2O. So I took this solid, apply plasma oxygen, and that plasma oxygen is going to chemically react with my organic photoresist, and it's going to make that solid into a gas and remove it. So in some ways, I chemically remove step number 9 with an oxygen plasma. Does everybody understand that? So I know through these presentations, we're discussing what is a plasma or whatever. So I want to reinforce that these plasmas are crazy cool things to know and very, very useful. We could also remove the photoresist, literally nail polish removers, acetone, the stuff you buy in Walmart or CVS, and that's how you'd remove that organic polymer, like the paint or a nail polish, right? And we could use acetone and IPA and DI water to remove photoresist. But once we do a process like etching, we usually burn it on, so it's really difficult to get rid of. So the wet chemistry method is not preferred. Actually, the oxygen plasma is probably a better, more concise way of cleaning up that photoresist from the wafer. So does everybody understand that? So basically, at this point, I'm just telling you to go over these 9 steps, which I described to you today. If you understand them, then today was a success. So I wanted to quickly, in the initial stages of this presentation, describe the whole describe the whole thing. And so basically now we're done. Like, you should understand lithography and all the steps. So we're done. So what we're going to do now is we're going to review this, and then each step we're going to talk about the intimate details. Does everybody understand that? So, at the start, going back here to the first slide, I wanted to show you this in general, maybe give you a little bit more general feel, like the second time, right? And now with my teaching method, this is the third time. And now what we're going to do teaching-wise is we're going to review these individual steps in detail so that you'll really appreciate them. Does that make sense? So I'm being literal here, and I'm certainly trying to encourage you to learn. I mean, that's part of my job. But these are things that people are going to ask you in an interview. And certainly if you could tell this story like I'm telling today, or replay this Zoom lecture, or, when you go into the lab, really pay attention and learn this, I'm telling you, you can get a job. Does everybody see that? So if you walk into a place and you're one of the very few in the general population that understands lithography, just this 3-hour presentation or 2-hour presentation, I'm telling you, boy, your chances of getting a job are just really good. So you want to understand this. Does everybody see? And it's not that hard. It's very interesting. So this is cool stuff. Does everybody see that? You can go, home or tell your friends, I could make things which mankind couldn't do, 50 years ago, as big as a virus, billions at a time, to make a cell phone. That's some cool science, guys. So, you're spending your summer in a good way, or attending these presentations, and it's really useful. And this should be like really interesting to you, right? If this isn't interesting to you, then I think you found out you don't want to be an engineer, man, because this is cool stuff. So I hope you appreciate it, right? So this is like a concert that only engineers get to listen to. Does everybody see that? So it's a blessing to have this background in engineering, because you can understand what other people didn't have. Make sense? So, being an engineer is really very, very cool. So you get to see things that other people don't appreciate. So I think that's beautiful. I think it's beautiful to learn art, to really appreciate art. I think it's beautiful to understand what food tastes like, or to match drinks to food and all that other stuff. I think that's really higher level, and it makes your life enjoyable. So I think being an engineer makes your life enjoyable. So I hope you enjoy your summer here, and I hope you enjoy this presentation. So anyhow, let's get back to that's my pop-up window. Stay focused, right? So there's a little pop-up encouragement window for you guys. So here's the photoresist. Resist is an energy-sensitive chemical spun onto the substrate surface that serves 2 purposes. It acts as a medium to absorb the pattern. So we put it on there, and it's basically like a liquid, but when we put it on and dry it out, it's kind of something that looks like maybe saran wrap, like a plastic sheet that just goes straight across the wafer. Is everybody seeing? So this provides protection for the unpatterned portions of the substrate. Since the resist is used in contact lithographies are light sensitive, they're called optical resist, or commonly photoresist. Does that make sense to everybody? So they're called photoresist because they're photoactive, which means they chemically respond to light. And they don't respond to all light. They actually have tuning agents in there, like chemical bonds, and these chemical bonds are going to respond to specific light. And the ones that we're going to look at the most in this presentation, which I'll talk about 3 times, is from probably the mercury vapor lamp. It has a spike in it where we have this energy-rich area due to the mercury vapor lamp constituents that's going to emit at 365 nanometers. And that's called the I line, and that's going to be our sweet spot. We use quite a bit for photoresist. So the photoresist itself is tuned for 365 nanometers. The organic chemists do that. So if you guys in this room or in these presentations like to be chemists, and that's your calling in life, and you really like organic chemistry, then go work for a photoresist company. This will be something that you could certainly do and make a living at, a very successful living at. And that's what they do. They make these photoresists that are actually tuned, organic polymers that are tuned to specific light. So the photoresist must have good adhesion mechanical properties, that it sticks well to the wafer. Does that make sense? And we're going to promote this adhesion by applying that HMDS coating, because we can't put this organic polymer on a wafer, because you wouldn't think about it, but that humidity, that water vapor is always sitting on the wafer. So we got to get rid of that to maximize the adhesion properties. So again, we're talking about this, these steps in detail, right? So I'm talking about the photoresist and how to put it on. So the photoresist, in modern fabrication, this requires high resolution capability, and the resolution capability is due to it's the smallest feature size, the smallest dimension that we could write on a wafer. And for my mercury vapor lamp, it puts out different peaks in there. Let me hold on a second. Let me unplug my charging cable that was getting in my way and bothering me. So can you still hear me? I got my microphone, make sure I adjust it. So anyhow, this resolution capability is due to the wavelength of our emission source. So for contact lithography, the most common source is the mercury vapor lamp. And the one that has like a decent peak, there's different peaks in this lamp, I'll show you later. But the peak that's the smallest wavelength with the best amount of energy is 365 nanometers. There's also one at 248, and that's a good peak, and it's even smaller, so you can make smaller devices. But the problem with that is the magnitude of that energy is about 20% of the 365. So that means that it would take us like 5 times longer to do the same work, because we have 1/5 of the energy. So we would have to do an exposure to get the chemical work done. We would have to expose the wafer 5 times longer, which means we would have to buy more machines, because we need to move these wafers or our substrates through the process. Does that make sense? So not only are we interested in the physics of lithography, we're interested in the manufacturing. And manufacturing, one of your most important things that you have to recall is time is money. Does that make sense? So a really good peak that has the appropriate amount of energy, so that we have a relatively small amount of time to do this procedure, which makes our machines more cost effective and our products cheaper. So we're going to go with the 365 line compared to the 248 line. And I'm going to discuss that again in a little bit. But I wanted to make sure that you understand that that's linked to the resolution capability, which is the size of the wavelength. And that's going to give us the size of something like the gate on a transistor. So we're going to be able to make, in this, with contact lithography, we're going to be able to make things that are about a 1/3 of 1 micron, the base dimensions on a transistor. Does that make sense? And again, as a review, to make sure you have these things in your mind, a hair is around 100 microns, and you could see probably 30 microns. And now we're looking at 10 times smaller than you can possibly see with your vision. Does everybody see that? So these are very, very tiny. And that's about as small as we could make with this contact lithography method. Does everybody see that? So there's 2 types of resist. The ones that we will be concerned with today, we're just going to stick with positive resist. But there's also the negative term, or the negative image of that, which is the negative resist. So the positive resist is the most popular. Historically, the negative resist had more health risks associated with them, and those health risks would be like birth defects. So right now, negative photoresist, I think, for the most part, most of them don't have that health risk anymore. They've designed new resists that don't have that. But for either resist, you want to be very, very cautious with them as far as health, because you are an organic polymer. Does everybody see that? So when you work with organic polymers, or organic polymer removers, or organic polymer modifiers on our substrate, we got to watch that we're not like breathing that stuff in, because we're organic polymers too. So those could be potential health risks. So I just wanted to make sure that we certainly have time to talk about health and safety in any presentation. So I wanted to make sure that you guys are aware of that, right? So just be cautious around photoresist and make sure you're certainly reading the MSDS sheets or SDS safety sheets on any chemical that you use in nanofabrication, right? So there's a little safety pop-up window for you, which I think is very important. So the positive resist, when we have the light, it comes down and it actually cuts the bonds in the positive resist. And negative, what it does is the exact opposite. The light's going to come to get down and link the bonds together. Does that make sense? And we could look at this through an analogy to give us a foundation. I know you could look at, like when you do photography, you could actually do positive and negative images. And in like Photoshop, you could do like just click a button and say positive and negative. Does that make sense? So you could change the tone. So instead of things being exposed, those would be the things that are protected from my mask. Does that make sense? So it would make the mask like in a reciprocal environment or reciprocal domain, if you wanted to look at it mathematically. Is everybody good on that? And the problem with the UV tends to be a little bit better. You can cut. When you do links, when you link polymers together, when you link them, it's like linking a chain together. And if you have chain links sitting on a table and you put them together, when you put the links together, that kind of like shortens the chain. Does everybody see that? So they tend to shrink critical dimensions. And that could be an issue sometimes because we're looking at things. Critical dimensions become important because we're looking at things that are as big as a virus. Does everybody see that? So that's, our scale in our mind is a little bit different than common everyday things, right? So the photoresist, when we look at it in detail, there's differences in photoresist. I don't know how many photoresists there are. Like how many types of rice are there? There's different types of rice, right? How many different types of apples are there, right? There's different types of apples. There's different types of all kind of different things, right? So photoresist, there's a lot of different, I'll call them flavors, right? But we're not going to eat them. But there's different types of photoresist. So they have different thicknesses, viscosities, different etch profiles. But for the most part, generically, if we approach them as a set, they have like some things in common. They have a backbone of polymers. They have sensitizers in them, and then additives. So we're going to discuss those things in detail. So what we're doing is, and now we're going to each individual step, and then we're focusing it on the details of each individual step or each individual item within that step. And right now, certainly a thing that we would like to detail is, what the heck is a photoresist? So that's what we're going to do right now. So let's answer these questions and break these things down even more, right? So divide and conquer. That's good engineering. So what is a polymer? A polymer is a large form or bulk form of collected monomers, which are individual repeating molecular chains. And as a chemical engineer, you might manufacture or come up with new polymers, right? Or consistently make polymers that are of the right length and the right viscosity for the application. So a good job if you guys are in chemistry and like organics, then your role in nanotechnology may be, or an option that you might enjoy because you like chemistry, might be working for a photoresist company. Does everybody see that? And photoresist, when you go to buy a quart of photoresist, it might be thousands. Did you hear that? Thousands of dollars. So that might be a place you want to work at. Does everybody see? Because there's money in it. Does everybody see that? And job security, because this is how you have to make, at least today in 2019, this is how we make our cell phone parts, et cetera, computers and sensors with photoresist. So it's always used, and we use it up in a process, and we got to replace it. Does everybody see that? So it's a commodity that is very expensive and very necessary. So it might be a good job market for you. Does everybody see that? Certainly, that might be, if you're chemistry guys, pay attention. So these polymers, they might be natural, like a protein, or synthetic, like a plastic, and we can make these things, right? Does that make sense? So I know that we had there's like the pear rubber tree, right? And that makes polyisoprene. So we can make that man-made, or we can get that from a tree. So they had, like in World War II, people really didn't know how to make that stuff synthetically, So that was really important to have those trees to make rubber tires and stuff like that. So that was something that made the Pacific Theater important, because those things are grown those pair of rubber trees, they're grown in like around the equator kind of stuff in those types of environments, right? So those could be natural or man-made. So now it's easier to make things man-made because we can, we have the knowledge to do that. So what's a sensitizer? Again, we're trying to go back to this thing here and break these words down. The sensitizer is a photoactive chemical in a resist that reacts in response to radiant energy in the form of light. So that's what we're going to do. We're going to kind of like tune my resist so that it actually absorbs the energy from a specific band. So that would be a specific laser or a specific peak in maybe a lamp. Does everybody get that? So that's what we're going to do there. And then additives, these are chemicals used to modify the chemical or light response. So once we capture them, then we're going to take that energy and we're going to do something like break the bonds, or it might be a dye that helps us absorb that energy. Does everybody see that? So if we have a dye in there, and that dye could be used as a capturing agent to utilize the most of that light that we have. And again, maybe one thing that we might want to think about is the reason we're doing that is certainly to make the chemical reaction. But a side thing is, when you think about that, we want to make the chemical reaction and be as efficient as possible so that my manufacturing steps are really quick. And that makes this more cost effective. And that's going to lower the price of like my cell phone. Does everybody see that? So these things are really, really important. So we can follow this cascade of ideas back to the organic chemist. So the organic chemist, when they do their magic and make really good photoresist, they're going to make photoresist that is like really high performance. And to define high performance is it's going to be really cost effective, so that we're going to be able to make our processors rather inexpensively, so that we can keep the price competitive against other brands. Does everybody see that? So everybody's in this race, whatever Android and Apple and, whatever Apple computers and Dell computers and sensors and, Toyota and Ford. So everybody's in this, technological race to make these components as efficient and cost effective as possible, because they want to provide a product that sells to the consumer. Does everybody see that? So these things go back to manufacturing. So we, as engineers, we in some senses control a lot of the economy. So when we do things that are efficient, we make things better for society, right? So this is a noble calling to be an engineer. So let's take a look at resist here. So the negative resist and a negative resist.
Can you go back to the sensitizer?
What's that?
Can you go back to the slide sensitizer?
Yes. So what a sensitizer does is, say we had one photoresist and we don't have a sensitizer in it. So what that sensitizer is going to do is it's going to actually help to capture the light. So often we could look at something like a dye or a sensitizer, and the sensitizer itself can capture, it'll be like bonds, and these specific bonds are going to be tuned so they capture that energy to make this process really efficient. Does that make sense? It's like a tuned circuit chemically. Is that good for you?
That's good, thanks.
Okay, could you turn your microphone off then? If I'll just remind you, not that you don't know, but when we leave the microphones on, and again, I'm not like, being rude, but then I get feedback here and everybody gets feedback. And if I had to identify what's the worst part about these lectures, then the lectures are really good. And I like doing this internet stuff because you get to talk to a lot of people and record it and everything and play it back. So I think it's wonderful. But that feedback stuff, oh man, that's crazy. And then I don't have the ability to draw, and then I use these like magic markers in the software, so that makes my terrible drawing even worse. So for me, the feedback and the ability to draw, I'm already bad at that, but then using those markers, oh my, that's the bad parts of these internet things for me, but might as well talk about that, right? So the negative resist, to get into these, these are the so this is the polyisoprene, right, that I talked about before. I think I said that the right way. Maybe I got that mixed up, so I don't recall. But polyisoprene is the natural latex that's the para-rubber tree, right? So we used to get this from trees, right? So we would bleed them and get this rubber component, and that's how people used to make, rubber back in the day, just like people, well, now we do the same thing with trees too, like here in Pennsylvania, which is a bit, people in the spring, they go up to trees and they pond these taps and they put a tube on there, these maple trees, and that's where you get maple syrup, right? So they bleed that sap out of there, then we boil it down and we get this organic polymer, and that organic polymer just happens to be really good on pancakes, right? But we could also do the same thing with a tree. We can tap into it and we bleed off this stuff, but it's not maple syrup. It's this rubber compound, and we would use that to make, along with nanoparticles, we would put a carbon, and that carbon black mixed with this polyisoprene, we could do something like make car tires. Does everybody see that? So there's a buy one, get one free nanotechnology example for you. So we would, we generally make these things now synthetically instead of using a tree, because you can get variance in that, and we can do things a little bit more predictable when we make it in a chemical lab. And that's what the chemistry majors are going to do. So these negative resists, like I said before, and I don't mind saying again, historically, these are the polymers that were a little bit more shady when it came to health. So you have to be really aware of any of these polymers when you work with them. But I always make sure that, I read, seriously, I'm not pulling your leg. I read MSDSs because you have to pay attention to that stuff, because it's a serious issue to get these health problems. And I'll just throw out there, I had cancer. You don't want to have cancer, boys and girls. It is very, very bad. It is wicked. So you don't want to, when there's cancer risks, you avoid them. Does everybody see that? So I'm not trying to get you afraid of resist. I'm not trying to get you afraid of organic chemistry, because people work with it all their lives. And if you work with it in the appropriate fashion, you minimize your risk. Does everybody see that? But you don't want to do things like take enhanced risk. So make sure you pay attention to safety. That is a very, very important thing for you guys to be thinking about, right? So negative resist, small amounts of developer are used, are required to develop negative resist, because the resists are soluble before UV exposure. Organic developer solutions contain xylene are often used. And so I hope that you guys recognize things like xylene and chlorobenzene. They're like universal things that are very, very shady and carcinogens. Does everybody see that? So these are these aromatic rings that are, have a lot of bonds available, and due to Murphy's Law, they're going to wind up in the wrong place doing wrong things for you. Does everybody see that? So again, to tell you this for real, you can go to Lowe's or Home Depot or Walmart and buy xylene or chlorobenzene. They have it at Walmart, they have it at Lowe's, they have it at Home Depot. So this stuff is around, and it is very, very serious thing, and you can get cancer from these things pretty quick. So you got to pay attention in life. Does everybody see that? So these things are around. So it's not just in the lab or the nanofab. These things are at Home Depot, right? So they try to minimize them. So, but they're still around. And again, let me talk about safety here. It's really important. You have to watch when you use this stuff. Don't put it in the groundwater. Does everybody see that? Don't pollute with this stuff. So when our labs, and certainly what you're going to learn, and what industry wants to see from you in the summer, your process going to university, is they want to see that you can handle these dangerous things and not, hurt other people, and certainly not hurt the environment, at large. So really, really important to pay attention to safety. Does everybody hear that? So I don't know what I'm here to, well, I do know what I'm here to teach today, but I'll tell you what I know is important to teach is safety, right? So always pay attention to safety. And I'll tell you what, respect, because this is what it just has to be. What gets respect on the job or an industry or something to mention in an interview is, I know how to be safe. Does everybody hear that? These are things that you must do. And these are things that are morally a guideline that we need to do. Does everybody see that? So certainly safety is very, very important. So something I want to talk about in any presentation usually is safety, right? So we also, when we get rid of things like xylene, we use generally alcohols to get rid of the xylene and all that other stuff. And importantly, we would use things like DI water. So I want to show you these things are occurring all the time. And I know that your training talks about DI water, but I want to highlight that these things are important. And then we generally get rid of water with a nitrogen blowgun. So these are important details. And I want you, when you go into the lab to do these lithography procedures, watch that you're doing this. Does everybody see that? So you should be able to fluently discuss the lithography procedure in a job interview, or to get into grad school, or to get your next internship. Does everybody see that? So these are foundational things in modern manufacturing, material manufacturing, that people expect you to know. So the negative resist, like I said, when we have these like links, and we can picture them as like chains in a links of a chain, when we put them together, naturally the chain shrinks, right? So this might be a problem. Sometimes this will give us jagged features and stuff like that. And then the resolution here gets to be a little bit more difficult than it is. And I know it's below 2 microns, but I don't know exactly what it would be with the zillions of photoresists that exist out there. But the negative resist sometimes are difficult to do with photoactive compounds, you know. So this is the chemistry, and this drawing shows you this polyisoprene monomer over here. And when we see these things like these pentagons, to me, from my limited chemistry background, right? So I teach material engineer, and I'm on the internet teaching this, right? And I think I told you this before. I'm moderately don't have a good chemical background. I wish I had more, but I'm really good at other things like plasmas or inorganic chemistry and other things and machines and all that other stuff. So I have my expertise, but it's not in chemistry, but I know enough to be dangerous. But you don't have to be an expert in every engineering discipline and actually be considered an expert. Does everybody see that? So hopefully I'm considered an expert, or I shouldn't be presenting today. But, you know, I got to tell you, because you're young engineers, you don't have to be an expert in everything. And it takes a while to be an expert, you know. And even when you're going to retire, so I'm headed to retirement right soon, you know, I can claim that I never was a super expert in chemistry. So have confidence in being an engineer, but don't be afraid of it. Does everybody see that? So that's something you should learn in an internship. So I'll say it explicitly to you guys. So when we look at, there's a nice cartoon next to my model of chemistry here, the polyisoprene monomer. We have the unpolymerized photoresist spread on the substrate. So the substrate is where the word unpolymerized is, right? So that's a cartoon. And then when I put my energy on there, what's going to happen, I mean, that's my photoresist. When I put my energy on there, what it's going to do is link these things together. So it shows that when I link it, it's going to shrink it. Does everybody see that? So negative is link and shrink, and positive, what shows goes. Does everybody see that? So those are good terms to get a hold of. So now let's look at my other photoresist, positive. So in positive resist, UV light causes the bonded polymers to break, making them soluble in the developer, known as a process called photosolubilization. So in this one, we're going to say where the light hits the polymer, it breaks it. So what shows, what hits the light, goes. Does everybody see that? So the light breaks the bonds. So there's two general types of polymers that we're going to use, or the backbone of the polymers. There's going to be the DNQ, because nobody in the world can pronounce that. I can't pronounce that on a good day, and today ain't a good day. And then there's also the chemically amplified deep UV resist, and that's too long to say. So we shorten these, and everybody would say, and one thing you want to learn in the summer is there's specific vocabulary that's used over and over again. And literally sometimes the vocabulary is so hard to say that we shorten it to like DNQ, or it's so long to say we shorten it to things like deep DUV. Does everybody see that? And then when you read papers, they should be explicit, right, and spell these things out. But often due to the limited amounts in technical journals, they might not define these things. And certainly in a textbook, they define them once, and then later on you have to understand what they are. So in the summer here, another thing that you should be thinking about is, what should I learn? And it should be vocabulary. Does everybody see that? So these are vocabulary terms that you should learn. So DNQ is a photoactive compound. And again, they're going to call these PACs, PACs, right? Before UV light exposure, the DNQ prevents degradation of the resist. After UV light exposure, the DNQ rapidly degrades, allowing the Novolac base, that's the backbone resin, to become soluble in a developer. And this typically would happen with 365 nanometer wavelengths. And that's so important that we define it as specifically eye line. So the word association here is 365 equals eye line. Does everybody see that? And when you go to pick a resist, you'll go to a catalog, and the catalog will have like chapters. And there'll be chapters like eye line. And there'll be the eye line resist. And they're tuned for 365. So does everybody understand that? So eye line is tuned, and that's a type of resist. So let's hear the polymer in the DNQ is the phenylformaldehyde polymer, also called phenylformaldehyde Novolac resin. And we all know that things like formaldehyde, they're poisonous too. Does everybody see that? So they're bad acting agents there. So you have to certainly be cautious of that. So those are things we want to take a look at here. And these DNQ resins, they're really good down to about 0.35 microns. And really in lithography, eye line in a contact aligner, which is my discussion for today, that's probably like for micro technology, like 0.35 microns. It's sub-micron because it's less than 1 micron. But that's probably like real cost effective, and the machines are, $100,000 or $200,000 or $300,000. And that's probably like the cheapest entry into advanced lithography that we can get. If we want to go below that to like 1/10 of a micron, then all of a sudden things are going to escalate into hundreds of thousands of dollars typically. Does that make sense? So beyond 0.3 microns, we start having a need for things like lasers and really more advanced lithography. So kind of in a step in technology, this is my opinion, right? But I think a lot of people would have the same opinion. Eye line is like old school and rather inexpensive or rudimentary, but it's impressive as all get out of town. I mean, it's impressive. But in the overall picture, looking at nanotechnology, which is insanely impressive, it's rather rudimentary. Does everybody see that? So it's kind of like pretty good. But most small companies are going to use things like Carl Seuss contact lithography. That's why I'm presenting it today. And it's really a very good way to get moderately advanced lithography, but not like sub-micron lithography. You're going to have to go with $1 million machines for that. But this is a really, really good lesson because it's going to give you 99% appreciation of running a stepper. Does everybody see that? So the contact lithography, and why I was asked to present it today, it's a buy one, get one free. Because when you understand contact, then you're going to understand steppers like BAM. Does everybody see that? They're really close cousins. And then the Novolac resin, so that you guys have something, it's the same thing as that you would use in plywood. So when you have that glue that's in particle board and plywood, that's a Novolac resin too. So the things in nanotechnology aren't that like crazy foreign. We see them in other areas, right? So they tend to be foundational things that we really super exploit in nanotechnology, and that makes us really cunning, right? So this is the positive resist chemistry. So we can look at the photo active compound, the DNQ, and we can also look at the backbone Novolac polymer right there for us. Does everybody see? And this is the reaction after the UV light. And basically what we're going to do is we're going to break these bonds, and then the UV light is going to produce this bond, and it's going to dissolve this area in here. So that's what breaks down. My polymer was all linked together in positive resist when I coat the surface. And then when I apply the light, what I'm going to do is do this chemical reaction, and I'm going to cut those bonds. And that's basically what I'm doing. Does everybody see that? So I have this photoactive compound, and then I do this reaction with the UV light, and then I break that bond. So then that bond is like cut. Does everybody see that? Or weakened. And once it's weakened, now I can remove it selectively with a remover. And the remover is going to remove the weakened stuff, but not the stuff that was not weakened, that didn't have the light hit it. Is everybody hip to that? Cool. So chemically amplified deep UV resist. We're going to talk about this a little bit later, but basically what this does is, if we have a wafer, and let me get out my pen. So I'm going to go back into, I'm going to do really terrible drawings for you. Does everybody see that? So let me insult you with my lack of ability to draw. So here's my wafer, and this is a perfectly round circle, so I'm laughing like this. Oh my. But this is a wafer. And on the wafer, we're going to do something like this with my mask. I'm going to, you know, at one time in parallel with my mask, I'm going to divide it up into something like this. It just gets worse every line I draw. How terrible. Oh my. Look at this. You're really going to have to use your imagination here, because I'm so terrible. Oh, it's going to take me forever to erase this too. That's even worse. So anyhow, this is my round wafer, and each one of these squares, I'm going to say, is a microprocessor. So like a Pentium chip. Does everybody see that? And basically what I'm going to do is, these on each chip, like so on each square, I'm going to have literally like billions of transistors on each one. And if I try to put my mask on here and align to this die and perfectly do an overlay so that these things that are as big as a virus can get matched up, so that I do one layer on top of another. When I do that, if you look at like the mechanical attributes of this, if I went down to this die down here, I'd probably be off by a hair. But when I'm off by a hair and it's so big, it's kind of like a moment arm. It's like a multiplier. So this one might be really good in alignment. But if I did this wafer all at once, then my mask on here at the bottom, let me do another color. So I don't even know how to do that. Let me go up here, format colors. So there's my color. I can't draw, so I try to pretend the colors help. But if, see this die down in here? Then that die wouldn't be completely aligned, and those chips would be bad. So that's kind of hard to do this whole wafer at once with a big mask like this. All at once, I'd have all my dies on there at once. And that's what I do in contact lithography. But in a stepper, I need the resolution to do things way submicron with perfection on every Pentium chip. So that's what a stepper is. So I'm teaching you what a stepper is. What a stepper is, I'm not going to have a big mask like this. I'm going to have a mask, and my mask is not going to do all the dies on the wafer. It's going to do just one Pentium chip. Does that make sense? So now what I'm going to do with that, and I'm going to switch my colors again as if it makes a difference. So I'm going to go to green or something. Now what I'm going to do is I'm going to apply this die, and I'm just going to write this one right here. And I'm going to do this one just one at a time, and it's going to be perfect, because I'm going to have perfect alignment. I can't have that if I do the complete wafer due to this like moment arm thing or mechanical kind of thing where I'm going to lose tolerance. Then I'm going to go to the next die, and I'm going to do this one perfectly. Then I'm going to use this, what they call a reticle. It's no longer a mask. We're going to give it a different name. And then I'm going to go to the next one, and I'm going to do this one perfectly. And then I'm going to step to the next one, and I'm going to step and repeat and go to this one and do it perfectly. Then I'm going to go to this one and going to do it. That's what we call a step and repeat. Does everybody see that? So with so I'm doing a contrast here. I'm talking about two different things at once. Hopefully it's not confusing. So let me go back to my colors as if that makes a difference. So what did I do? Colors. Oh my, it's hard to do it. Was it this color here? So this right now is a mask. And a mask does all the dies at once. But the problem is I have to do rather big features because it's hard to get alignment across the whole wafer. But if I want to do smaller ones, let me go back to the colors as if this makes a difference. What I do with smaller features is I do a reticle, so I do them one at a time. And then I get more perfection because then I'm using a smaller reticle, smaller mask, and I can do perfect alignment. And that's how you have to do Pentium microprocessors, or the microprocessors that are in your cell phone. Does everybody understand that? So you have to use steppers because you need that really good resolution and alignment. So now my question is, we're talking about this photoacid generator and why do we need that? So this is a big, long story. So I'm getting back to that. So what's the problem here? The problem is, now that I have this high resolution and I'm doing one die at a time, instead of doing the whole wafer in 6 seconds or whatever time it takes, now each die is 6 seconds. So 6 seconds and 6 seconds and then I got a minute, 2 minutes, 10 minutes. So that before, this wafer used to take me, if I do it with contact aligner and do a mask, it might take me 6 seconds. Does everybody see that? So I do a wafer in 6 seconds. My production line is really fast. Does everybody see that? Look at like the Ford assembly line making cars. Does everybody see that? I'm making like a step in 6 seconds, send it down the line, making my product. Does everybody see that? So 6 seconds is a pretty good number. So I can do, dozens of wafers in an hour. I can do a lot. So 6 seconds is really styling. I like that number. But now my wafer all of a sudden is going to take me 6 minutes or 10 minutes or something like that. Then what do you say? Well, to keep my assembly line moving, all I have to do is buy more steppers that do this in 6 seconds. And a stepper's $35 million or $50 million. So now what did I say? I have a technical problem, and the technical problem means I need high resolution. So that means I have to take more care and do each individual step. This all makes sense. So I do that. But now all of a sudden, this wafer to do that one step in lithography is going to take me tremendous amount of money. And now my cell phone parts are going to be insanely expensive, and computers are going to be insanely expensive, and cars are going to be insanely expensive, at least at my company, if I don't resolve this problem. So now as an engineer, I got to say, how do I make this cheaper? And so I have some options. Well, I can't do the whole wafer at once because I just can't do that. I still have to stick to the single die at a time. So what I can do is I can change my resist so I don't do an exposure in 6 seconds. Maybe I can do an exposure in 1/10 of that time. So I still need to get that amount of work done. Does everybody see that? But now what I want to do is, the work is often time multiplied by energy. Does everybody see that? That's called a dosage. Time multiplied by energy to get the work done. Before, we had a moderate amount of energy and it took 6 seconds. Those coupled together would give me this development. Does everybody understand that? Now I have the problem that I want to get that work done, but I want to reduce this time, which means when I reduce the time, I have to increase the energy. Does everybody see that? So I have a couple options to do this. I can increase my light energy, and we do that. Answer number one. The other answer is, and what we do with deep UV resist is, we do like a sleight of hand. We trade energies. So instead of just doing light energy, we do light energy and it sets up the response. We do work with light, and then we finish it with heat later on. So basically what we're going to do is, let me go to colors here. Well, I'm going to do this die with light energy, but I don't do the full process. Then I do this die with light energy, but I don't do the full process. Then I do this, but it's really quick. Does everybody see that? Then I get done with my wafer. Then let me go back to my colors here, as if it matters. Format, color. I'm going to go to this one, this red. So we'll say that that's heat. Then I finish this whole wafer with the green, and I did each one. Then what I do is I go like this, and I put it on a hot plate, and I heat up the whole wafer at once. and that finishes the process. Does that make sense? So let's go back and redefine what deep UV resist is. It's a resist that takes a short amount of time. I set up the reaction with light, and that means I use a very small amount of time, but I don't do the whole process. But later I finish the process on a hot plate, and I make it very inexpensive. Does everybody see that? So that's what deep UV resist is. It's a rather, deep UV resist is a rather complex story, right? So we have to understand manufacturing. We have to understand, we can trade off light energy for heat because we're looking at a total over, to get work done, we need so many joules or kcals, however you want to, quantify energy. But we can replace, that work to get the total procedure done. We can divide that into, we give so many joules of light energy, and then later we finish the process with so many joules or kcals of heat energy. And that gives us a total energy to get that work done. And the work that we're going to get done is this localized development or localized change in photoresist to define a pattern. Does everybody get that? It's a really kind of a complex story, And now what's my new story? I got to erase all this stuff on the wafer. So this is going to take a while. Oh, here's my eraser. That ain't bad. Well, all these little things are going to take a while. It's not that bad. It's like a break. Give your mind a rest. Oh, that stuff went away really fast. I'm really surprised.
Sorry?
Yeah.
Can you explain the slide again? I'm so sorry.
The whole slide.
No, like starting from the part that is get 6 seconds, something like that.
Yes. So let me go through, and I'm going to try to do that within the presentation. I'm going to review this again. So maybe that question will be answered when I go further through here. Does that make sense? And then I'll go back and review that again. So I'm going to hold off on answering your question because I think I'm going to answer it. And then if I don't, I'll come back and do it again. Does that make sense? Is that? So if you can turn off the microphone, that would be great. I can see that on my screen. So let me get rid of my eraser. So let me see. I'm going through the answer. I'm seeing where I can answer your question later. Well, let me answer the question now somewhat. So we're going to use 365 nanometers. So this is a mercury vapor lamp, and this is the energy peak right here. Do you see in blue? That's the energy peak. So this energy peak right here at 365 nanometers, I'm going to apply that energy to my wafer, and that amount of energy times like 6 seconds is going to give me the energy, this peak times time is going to give me the dosage, that's the amount of work to actually make my photoresist bonds break. Does everybody understand that? So what I could do is I can take this energy and I can apply it, but over a very short time, and then I didn't do my total work. Does that make sense? So I didn't finish my job. I can finish the job by putting it on a hot plate, and therefore I'm breaking up the energy into light energy and then heat energy. Does that make sense? Is everybody good on that? Maybe I'll make up an analogy like a story. Say I do something like, doesn't have anything to do with nanotechnology. I'm going to go back to the kitchen, and I'm just going to tell a story, and hopefully the story makes sense. So say I heat up in the morning, I go to my stove, my like gas stove, and I put my water pot on there, and I boil my water to make tea. But I don't boil my water. I don't heat it up all the way. And then I pour my water in with my tea bag and my cup, and I look and I'm like, hey, there wasn't enough energy to get my tea to steep. So do I necessarily need the stove? No, I can go to another energy source. So now I open up my microwave and I put my teacup in there and close it, and then I push the button, and then I heat it up for 20 seconds, and then my water boils. So I broke up making my cup of tea into 2 steps. Heating the water a little bit on the stove, and then finishing the process with my microwave oven. Does everybody see that? So my analogy here with the deep UV resist is, I don't do all my work with light. I like warm it up with light. Does everybody see the analogy with the tea? And then I finish it, not in the microwave, but on the hot plate. So why do we do this? So let's go back to my, I hope not confusing analogy. That frees the stove up. The stove could do more tea. Does everybody see that? So now I make my production faster because I broke down this work. The work that needed to be done was boil my tea. But I broke it up into 2 sections. I warmed the water up, but then I finished it in the microwave. Does everybody see that? But that allows me to get more like cups of tea done on my stove. So I broke it up into 2 things because in my analogy, my stove is $35 million and I can't use that much. I can't afford many stoves, with my tea bag analogy. Does that make sense? So who was in the room there at NSU? Does that analogy help answer your question? Did you understand that? So I seen a thumbs up. Does that make, because I can see a guy, but I can't see the girl because the picture's like this big on my screen. But that answered your question. Is everybody good on that? So a thumbs up. Great. I hope that did. So, I think we're going to review that when we go through the presentation, but knowing the answer and then reviewing is better than just learning it the first time. So, hey, thank you very much for your question. How about that? So that's going to help us there. So now I got a new analogy making tea. Oh, I'm going to have to take a break soon. So let me think about that. Let me look at my cell phone. So it's 10:30. We're on to a break in a little bit, so I'll take a break soon. And the reason is I want to actually have a cup of tea. So I'm going to make, I made a cup of tea. It's sitting in my microwave. I'm going to reheat it. I made some red tea. I like red tea. Well, I like all tea, but in the mornings I like usually black or red tea. As if you care, but. So the chemically amplified resist, what we're going to do with these is it's a 2-step process. And it's a 2-step process because of that crazy drawing I did. We need to have the resolution on each individual die, so we can only afford to do one at a time. If we try to do the whole wafer, it won't be near perfect. So what we do is we focus on one little piece and make it really, really perfect. Does everybody see that? I don't know an analogy, but it would be like making a really high precision painting. We wouldn't do that with a big paintbrush. Does everybody see? We need a real fine paintbrush to do our work. So we just have to do things real precision and focus on a little area to make it high performance, right? So I hope that analogy makes sense. So the deep UV resist, what we're going to do is we're going to expose each die for a short amount of time, but that time is not sufficient to get the whole procedure done, but it's going to set up the procedure. Then what we're going to do is take the whole wafer later on and put it on a hot plate, and the hot plate is actually going to finish what we started with the light. Does everybody see that? So this is called like a 2-step process, and we need it for more of a stepper. So we're doing contact alignment is this presentation, but I did want you to know about this stepper thing, and I did want you to know about deep UV resists because they're phenomenal in industry because they save money. Like literally, your cell phones would cost a lot more if we didn't have deep UV resist. Does everybody see that? This makes modern manufacturing a lot more cost effective. So if I were to look at to tell a story, so I'm telling the story about manufacturing. If I were to look at like semiconductor manufacturing, and somebody asked me, because it's my field, they would say name like 10 things that are essential at minimizing the cost to make microprocessors. I would certainly always say DPU resists are super important to keeping the cost of microprocessors under control. Moore's law, etc. Does everybody understand that? So you might think that this is because you're not aware of this background. Once I tell you the story, you're certainly aware. But I'm not talking about gobbledygook, sciencey stuff for no big reason. This stuff is like important. Does everybody see that? And then for you to select a job, if you like organic chemistry and stuff, this is a field to be in because it's really important. It's a critical step in semiconductor manufacturing. So this is a technique or a concept, maybe a concept that you only understand when you're well schooled in nanotechnology and lithography. So it's an important lesson to be learned. So I'm glad to tell you that today, and I hope you get an appreciation for it, because literally this is very, very important. Like I said, if I were to name 10 things that are important in semiconductor manufacturing, I would say a detail that's really a big kind of thing is this DPU resist. It's big time. It's very big time, So this is the chemically amplified DPU resist, and this goes over the details of that. But basically what we do is we apply it. We start so we apply it, and then inside the chemically amplified DPU resist, we got this thing called a chemically photoacid generator. So the photoacid generator is embedded in the resist, right? And the photoacid generator is step one to get our work done. So it's sitting in there. The light comes on, and it actually turns the switch on chemically in the photoacid generator. And the photoacid generator is weakened by the light. And that starts the step. And we can do that in like a second. Does everybody see that? But the process is not finished. It's just started. Then what we do is we put that on a hot plate, and it finishes that process, because we look at chemical properties are often completed and understood with the concept of like the Arrhenius equation, right? And that's basically E to the K, which is the Boltzmann's number, to the T, right? E to the KT. So T, it's an exponential number, and that makes this process quicker. So we're using this heat process to finish this, which was started with light by this embedded photoacid generator. Does that make sense? So that's why this is a two-step process. The light activates the photoacid generator, and the acid is an E to the KT thing, and it's finished by the heat. And then that acid is going to break my bonds. Does everybody see that? Or make my bonds or whatever. So that's going to be my bond modifier. Is everybody see that? So that's this drawing. So I'm going to ask you now to think about my discussion over the last 15 minutes, maybe, because it was a complex discussion. This is why I'm allocated 2 or 3 hours to do this discussion, because this is very complicated. Does that make sense? So it's a story within a story. So we have to understand about chemical reactions. We have to understand about light. We have to understand what photoresist is. We have to understand the big picture of lithography. And then once we understand those, we can understand these details and appreciate what chemically amplified DPU resists are. So this is a story embedded in a story, and it can be confusing, right? I mean, this is, so I'm trying to take the time necessary to do this. So, hopefully I'm being successful, but an aid to my success here is this picture. So please understand what this picture represents, and that my words should convey this picture, right? So a picture's worth 1,000 words. I hope you understand this picture. So again, our goal is we want to do lithography in the most fast, efficient way, precise way. This is, really the discussion of nanolithography. We want to do, a virus level precision, billions at a time, quick, like lightning quick, and that's a lot to ask. Does everybody see that? So that's the question, and the answer is understanding this process of deep UV resist. Does everybody see that? So it's a rather unusual question that you have to know about lithography to understand the question, and then the answer, you again have to understand the concept of lithography, but also about chemistry. And often what we do in engineering or in work, we do two processes at once, right? So a lot of times we do chemical and then we do heat to help the chemical. Does everybody see that? We can see that when you do laundry, right? So you use your detergent and it's so effective in cold water, but if you apply warm water, it makes that detergent even more aggressive and it'll clean your clothes better. Does everybody see that? So that's a two-step process. We use the chemical affinity of the surfactants like the soaps, but we also, in some places, like exponentially help that process by applying heat. Does everybody see that? So we do that. You do that in cooking, right? So you have these chemical reactions, and we help these chemical reactions in an oven, etc. So these things, these are throughout engineering or throughout life. So, you might not see that, but this is certainly to see the forest for the trees. This is what engineers understand, right? So this is the chemically the DPU resist, and we would use these more when we use like excimer lasers and stuff. We would go beyond the resolution capability of the mercury vapor lamp, and we would use things like lasers. So these are typically exposed when we go more submicron into quarter micron dimensions or below that. Right? Does everybody see? This is really the land of steppers, and these things come into play because we need that resolution is so small. We're really starting to make things that are tiny, right? And then because they are so small, we would need to have the overlay resolution of the mask to lay on the previous layer. And then we need to have this precision and also the accuracy, right? So that those things are really a lot to ask. And so now what we're stopped at is the primer technology. And I'm looking at my phone, and I'm looking at the time on my phone. And that's about halfway through my presentation. So what I'd like to do now, just to give everybody a break and myself a break, right? So my voice is getting a little hoarse. I want to take a 10-minute break or so, and then we're going to come back and complete the presentation. So I'm going to have a cup of tea, and then we'll get back here in 10 minutes, which would be about 10:55 or so. Does that make sense to everybody? So we'll take a break there, and I'll see you in about 10 minutes or so. Is everybody good? So thanks for your, watching my presentation. We'll take a break so we'll be fresh and come back and learn some more. Take care, guys. Enjoy your break.